Okay, welcome to the last part of the Labor Day E-Day lecture series, the third video. So for this part, we're going to talk about half-life and doubling time. So let me jump right in with those definitions. Half-life is the time t that it takes for p of t to equal 1/2 of our original value. Okay, it's the time t for us to have half of what we started with left. Okay, doubling time is the opposite of that. It's the time t that it takes for p of t to be equal to twice our initial value. Okay, so these are the definitions for half-life and doubling time. All right, so problem 4 is going to ask us about doubling time, and then problem 5 will ask us about half-life. So let's jump right in. Problem number 4 says, a new virus was discovered at the biology department of the University of South Carolina. Something about a grad student, they dropped something and the virus was became uncontained and 15 people got sick. Okay, so the main thing that I'm reading here, 15 people got sick on the first day. That tells me P naught equals 15. And then they tell us 7 days later, there were 94 people infected. The way I should read that is P of 7 equals 94. Assuming that the spread of the infection satisfies an exponential model, we want to find a formula P of t for the number of people infected t days after the outbreak began. So we should be looking for an equation of P of t equals P naught times a to the power t, where we're not quite sure what a is yet. Okay, well, we can figure out a. It's not an issue. We know that 94, let me write it in a different place. I'll write it down here. 94 is equal to P naught, that's 15, times a to the power 7. Okay, a to the power 7, because it took 7 days for us to get 94 infections from 15 infections. So this means that a is equal to 94 over 15 all to the power 1/7, which is something like it's close to 1.3, so we're going to use 1.3. So we can write down our equation now. We know P of t is going to be equal to 15 times 1.3 to the power t. Okay, so now we have a formula for the number of infected people t days after the outbreak began. I do want everybody to notice that in this problem, t is being measured in days, not years or months like we've been doing so far. So just remember that. Okay, now they ask us, what is the doubling time of the number of infected people? Well, if P naught equals 15, double that is 30. So we want P of t equals 30 using my equivalent notation for P of t. Just going to fill that in. 15 times 1.3 to the power t. Now I want to figure out what t is. So simplifying by dividing 15 on both sides, I get 2 equals 1.3 to the power t. My unknown is in the exponent, so that tells me I need to apply a logarithm. we get ln of 2 equals ln of 1.3 to the power t equals t times ln of 1.3. Divide both sides by ln of 1.3. We get t is equal to ln of 2 divided by ln of 1.3. And that's equal to 2.641 ... days. Okay? That makes sense considering that we're told 7 days later we had 94 people infected. We've done more than double. We've doubled twice and then some in 7 days. So if our answer is telling us that we doubled in 2.6 days, that's consistent with what I am picturing from the word problem. Okay, so that's how we do a doubling time problem. Now let's try a half-life problem. A can of mountain condensate has 55 milligrams of caffeine, leaves the body at a continuous rate of 14% per hour. Okay, keyword here being continuous. So this tells me K is equal to negative 0.14. Why negative? Because it is leaving the body. Okay, leaving the body means it's decreasing, so K is going to be negative. And 55 milligrams, that's going to be my P naught. Okay, so we want to write a formula for the amount A. So really we shouldn't say P naught, we should say A naught. Of the amount of caffeine left in your system T hours after you drink 1 can of soda. Okay, so we chug a can of Mountain Dew. We immediately have 55 milligrams of caffeine in our body, and we want to know how much caffeine is left after T hours. So we're looking for an equation of the form A of T equals A naught e to the KT. Well, we already figured out A naught and K, so it's just going to be A of T equals 55 times e to the negative 0.14 t. That's going to be our equation. So now we're asked to find out what the half-life is. So the half-life is going to describe the amount of time that it takes for there to only be half of the original amount of caffeine left in my system. Okay. So what we want is the time T such that A of T equals 1/2 A0. Well, A0 was 55, so that means 27.5. So 27.5, that's A of T. That can be set equal to the right-hand side here, where T is still unknown. So we'll write 55 e to the negative 0.14 t. Divide both sides by 55. We'll have 1/2 equals e to the negative 0.14 t. And now what can we do? We can take the ln of both sides to get the t out of the exponent. So we'll do ln of 1/2 equals ln of e to the negative 0.14 t. And now we see the convenience of using this model where we have e to the power k instead of a. Because when I take the natural log of the right-hand side, which I'll highlight in blue, I'm doing ln of e to some power. When I do that, all I have to do is take the power down, and that's it. So this is telling me that ln of 1/2 is equal to negative 0.14 t, since e to the x and ln of x are inverses. So now I just divide both sides and I'm done. T is equal to ln of 1/2 over negative 0.14. And we can go ahead and calculate that out to get our answer.